Okay, so now let's look at last part of week 2. So part 5 will be dealing with limitations of linear classifiers. Notice that this is not just the limitations for perceptron itself, but actually these are the limitations shared by other linear classifiers as well. As we said, all linear classifiers have the same model formats at testing time. Basically, do the same kind of computation, just dot product and take the sign of the result of dot product. So they all share the same limitation. That is, the decision boundary has to be linear, has to be a single line. They cannot do any nonlinear separation. So we will see a classical example of XOR dataset, which kind of effectively killed the research of perceptron for 30 years. And then we'll talk about the ways to alleviate that problem, basically by adding nonlinearity. And the simplest way to adding nonlinearity is to introduce a feature map, which kind of maps input from low dimensions to higher dimensions, using some nonlinear functions, and on the higher dimensions, the data set becomes separable, and which you can map down back to lower dimensions. Eventually, you have to redefine what is linear separation under a feature map. Okay. So XOR. So this data set is just notoriously bad because regardless of how you try, you just cannot separate it with a linear line, right? So there's no way to do it. And there was a book published 10 years after perceptron was invented. So perceptron was invented by Rosenblatt in 1959, and Minsky and Papert wrote a book in 69 called Perceptrons, and they proved that not just XOR is not linearly separable, but also like finding the minimum error linear separator for a general data set is NP hard. Okay, NP hard, for those of you who are computer scientists, NP hard just means very, very difficult, that there is unlikely a polynomial solution to it. So this result effectively killed neural networks in the 70s, because, and especially perceptron was dead for 30 years until Frohn and Shapiro revived it in 1999. Okay, so what happens if the data is not separable? Well, in practice, data is almost always inseparable. Well, what does that mean exactly? As we say, that if you can add a feature map, you can kind of magically make a non-separable data set separable in some higher dimensions. So really, the notion of separability depends on your choice of feature map. At the end of this lecture, we'll kind of redefine linear separability under feature map. But just, for now, just keep in mind that it doesn't make sense to say this data is separable or not, right? It has to be separable under what feature map. But if you just say the data itself, that means you're using an identity feature map, right? So you don't transform the data. But in reality, if you work on any data set, okay, if you want to apply machine learning to anything, you have to define a feature map. You have to do some pre-processing of the data, right? And you understand what that means if you work on homework 1 in week 3. So there was another theorem called perceptron cycling theorem, 1970, that says if the data is not separable, the weights will remain bounded. It will not diverge. It will not, like, say, go to infinity. It will remain bounded and will cycle. Okay, so there was a mini problem, a small problem in exercise 1 that asks you to verify this theorem on XOR dataset. And what we do in practice if the data is not separable, because if the data is separable, we'll see eventually the training error goes down to 0, although that doesn't mean anything, right? Because the test error or generalization error will actually go up. But if the data is not separable, then even if we train it forever, we're still not going to see the training error goes down to 0, right? It will just cycle at a very, very low rate, like say about 5%. You just cannot improve upon 5%. Now, what we do in practice is always use a dev set for early stopping to prevent overfitting, right? So this dev set is also called a validation set or development set, right? To simulate kind of unseen data. And yeah, the feature map that we can transform the original problem that is inseparable in lower dimensions to separable in higher dimensions is kind of a special case of a more systematic method called kernels, which we'll cover after SVM in week 5. Okay, so let's look at this very simple example of XOR. Now, let's add one more feature, that is the combination of x1 and x2, and suddenly in 3 dimensions, the data set becomes trivially separable, right? Because these two squares, these two, say positive examples or whatever, or square class, become above the xy plane, so they have a z of 1, and the circle class will get kind of sink underneath the xy plane. They have a z value of -1 in the 3rd dimension. So adding this feature of x1, x2 magically solve the problem. Trivial, right? But notice that this is already nonlinear. x1, x2 is a quadratic term. It's a quadratic feature, so it's no longer linear. So this, as I said, is a special case of more general notion of polynomial kernels. So if you combine 3 features together, that's basically using a cubic term. So if you combine 4 features together, that's kind of quadratic. That's called a 4th order terms or whatever. Okay, so let's look at more examples. So often you have like a non-separable case in 2 dimensions, and you transform it, it becomes linearly separable in 3 dimensions, like in this case, right? Or in this case, and then you will have a linear decision boundary, like a plane, xy plane, in 3 dimensions, and then you project it back to lower dimensions. It becomes a non-linear decision boundary in 2 dimensions. For example, a circle, right? A circle here. So remember that really what happens is that in higher dimensions is you're still doing linear separation. You're still training linear classifiers. You're still training perceptron. It's just on a different dimension, in a different kind of representation, right? Okay, so there's notion of cursive dimensionality, which basically says the higher the dimensions, the more dimensions you have, it's harder for you to learn. But actually here, the more dimensions you have, the more likely you're able to separate the data. Okay, it's always the more dimensions, the better. Okay, in terms of separability. Okay, so here is a very nice demo. So you have a non-separable case, and you project it using a polynomial kernel into 3 dimensions. Okay, from 2D to 3D. Now the points will kind of move up, and then in this new space, it's separable by a linear space, by linear separation boundary. Okay, and then project that linear boundary back to 2 dimensions. It becomes a circle, right? So that basically summarizes what I said on the previous slide. Okay. So this is something that SVM with kernels always do, which we'll see more in weeks 4 and 5. But just for now, you got an idea, right? So now finally, let's redefine linear separation. As I said, if you say the data is separable or not, it really depends on your feature map. So it doesn't make sense for you to say the data is just not separable. Well, you haven't tried feature maps yet. What if you just try some other more complicated feature map? Then the data becomes separable, right? So it doesn't really make much sense practically, right? Even though it's theoretically you can say the data is separable or not. You're using identity feature map. That means you don't even need a feature map. In reality, you always say the data is separable under this feature map. The data is not separable under that feature map. Okay, and it's not a case that if I make it if I make it separable, it's always better, because you can make data sets separable by using more and more complicated feature maps, right? But that's kind of overfitting, right? Because as I said in week 1, overcomplicated model can remember idiosyncrasies or outliers, can fit to those kind of not unnecessary details in the training data, but it doesn't help you in testing time, okay? Anyhow, we have to redefine separation and the convergence theorem. We don't need to reprove it, but we have to redefine. Okay, a data set D is said to be linearly separable. You insert a phrase under feature map phi if and only if there exists some unit oracle vector U, which magically correctly classifies every single example xy in that data set D with a margin at least delta. So now you change this definition of what does that mean to be correctly satisfying. Example x, you just change x to phi of x. That's a drop-in replacement. That's why if phi is identity map, then you don't need it like what we did before. Then the perceptron must converge to a linear separator after at most the same number bound of mistakes in the worst case, where R needs to be redefined to be the max over phi of x, so the features, right, after feature map. Okay? And in practice, the choice of feature map, also known as feature engineering, is often more important than the choice of learning algorithm. You will see that after you learn like SVM, Perceptron, and logistic regression, they almost all perform roughly the same. Okay, very small difference. Okay, but if you change a feature map, then all these algorithms change. If you use a more complicated feature map, all these algorithms will do better on training set at least, right? But the actual difference in terms of error rate at training time or testing time is not too sensitive to the choice of learning algorithms, but it's more sensitive to the choice of features. So you will spend more time on feature engineering, right? So at testing time, do not forget to transform each input into 5x as well, because you're trained on 5x space. So trained on higher dimensional space, you have to test on higher dimensional space as well. And you might think that feature engineering is boring. It is boring, right? You have to try a lot of different things. You have to try, say, feature combinations, x1, x2, x2, x3, x1, x3, and so on and so forth. But deep learning, the forefront of machine learning right now, aims to automate feature engineering. So in the old days, well, machine learning already is automating automation, but deep learning is automating automation. What does that mean? Well, computer science is automation, machine learning is automating automations, and deep learning is automating automations. So automation to the power of 3. What does that mean? It means that the features is also learned. It's not set by the programmers. In classical machine learning, you define the features, you transform the data from low dimension to high dimensions, and then you apply the machine learning algorithm. Deep learning says, no, the representation also needs to be learned. That means the features also needs to be learned together in an end-to-end way, so that by backpropagation, your features can also be improved. Okay, so maybe for certain tasks, these features are better. For the other tasks, those features are better. And you don't want to spend the time to experiment manually. You want to just let the machine learning algorithm figure out the best feature map for your data set, for your particular problem automatically. So that's why it's automating machine learning. And that's why we say deep learning is automating automations. Okay? So I think that's the end of week 2.